Okay. Hi, everyone. So this is a video of the 3T scanner being delivered to Li Ka-shing. This is Li Ka-shing building. This is Oxford Avenue, and that's I guess the concrete plate, in front of the Li Ka-shing. And this is what happened during that day. The concrete plate has been lifted and then put on the road. Guess who's blocking Oxford for traffic? And all those angry people on Saturday. Yep. And then they go and the magnet actually comes cold, so it's actually filled with helium. And they trucked it from from Atlanta, like from Georgia, all the way to here and on a truck. And so it's cold. It's not ramped up, so it doesn't hold a magnetic field, but it is cold. It has liquid helium in it, and then they dropped it in this hole over there. And if you actually go over there with your phone and run like the Tesla meter app that most of your phones should have, you should be able to figure out where is isocenter underneath the concrete, both for the 7T and the 3T, because they both have actually field that extend outside, albeit very small, but still, it's bigger than Earth field. And then they took the concrete slab and closed it. That's it. So of course, while we were waiting for this thing to happen, the what do you call this thing that lifts the crane? The crane broke, so we had to wait till they fixed it. It was pretty frustrating. There you go. Wonderful. And then I wanted to show you this. So then the scanner arrived, and then they went ahead and wait. That's not what I want to show. Oh yeah, it is. It was. Mm, there you go. Okay, so then the G folks, the G engineers went and started to ramp it up. In order to ramp it up, it's actually quite interesting. Well, let me just kind of give you an idea of what's actually going on. So effectively, you have this inductor that you drive current through, and this is made out of a superconducting material. So what you'd have is you'd have a power supply, and then you take its plus and its minus, and you connect to here, and then you start driving current in that thing. And you start driving current and current and current, and then once it reaches the field, what you're actually doing is this. There's a heater that heats this this part over here. So that is not superconducting when it's hot. And then once there's enough current flowing through the coil, what you do then is you would cool this part, and then slowly but surely it will close this, and then because it's superconducting, then current will just keep on flowing. Okay, that's kind of like the idea of how you'd go and ramp this thing up. So you heat it, and so this opens up, and then you can drive current this way. And then once you cool this, then it connects, and then it becomes a magnet. So that's the idea. And for that, they have a few pieces of equipment, which is also interesting. You see there's this cable that's connected to a power supply. This is the ground, I guess, and this is the red, which is the plus. And then this is connected to this electrode. You see this big copper electrode. And this big copper electrode is actually dropped into inside the scanner. And actually the bottom of it touches the superconducting coil. Okay, so this is all, they put it inside the helium, this thing. And then they start pumping current into that thing. While they're doing this, they have a probe inside the magnet that measures the magnetic field, and they have a magnetic field monitor that monitors what the field is. Okay, as you increase and increase and increase. Okay, that's kind of what's happening. And then this is a video of the GE field engineer putting that the electrode into the magnet. So take a look. This is Miguel.
Right.
And I have to say, he was very nervous. It was the first time he was doing this. I had another person that does that all the time, and the other person does that all the time, hates doing this because it's super scary. And so he gave it to Miguel to do it. And Miguel, look how uncomfortable he is. Okay, just so you understand, and how I am uncomfortable that he's uncomfortable because he's messing up with my scanner. Hold on.
Right.
He's not happy.
Here we go.
You kind of see why he's uncomfortable. Because he has to open that thing, and usually cold liquid helium pours out of this thing. Okay. And then he had to put the other one,
Is that good enough?
Poor Miguel. Okay, and this is the power supply. And at some point it was pushing about 400 amps with 5 volts across the coil. So that is 5 divided by 400. You can figure out what is the resistance, I guess. It's pretty small, right, in terms of ohms. So 5 divided by 400, that is probably 1 over, like basically 100th of an ohm, approximately 100th of an ohm. So it's pretty low, and you can kind of figure out like how much power is being deposited into this thing. It's about 2,000 watts being deposited, all the time, to ramp this up. And then this is when the actually field went all the way to 3 Tesla. So you can kind of see here. And this is what's going on. So they always have to release helium while they're ramping it up, because there's always a chance that there's going to be some energy will go into the helium, and the helium can, basically evaporate, and that could release a lot of force. And so they pretty much let it kind of, drip. And as the liquid helium comes out, it actually freezes the air, because the liquid helium is 4 degrees Kelvin. And so the oxygen and nitrogen in the air actually freezes, and there's air snow being built over here. So it's called air snow. And then here's the air snow being poured into a cup, and I was pretty happy about it. That's air snow. Oh, and then I went and threw that air snow on the floor, and of course it evaporated immediately. Yeah, I mean it's solid oxygen, right? That's actually pretty scary stuff, by the way. You don't want to put it next to a flame or something like that. It's pretty terrifying material, solid oxygen. Okay, it's rockets, use that kind of stuff. All right, hope I impressed you with this piece of technology that is used, and so you can kind of imagine how why these things kind of can get expensive and complicated. It's a lot. It's definitely an engineering feat to actually do this. All right, any questions last time? No? Any questions? No, no? No? Okay. So just wanted to go back and just remind you of a couple of things. So first of all, I want you to remind you that the way we model RF uses excitation K-space. Okay. We have, if you remember, our K-space is always the area of the remaining gradient, and then you have a truck full of RF that goes and deposits RF in K-space. And if we want to analyze then what is the slice profile, then once we know what the RF is on K-space, we can take a Fourier transform and then see what the slice profile is. But there's one thing I kind of want to show you is the following. If you actually see what's going on here. So here you have GZ, and then you have RF that's being deposited, right? So if we go and deposit this RF onto K-space, so this is KZ, now we deposit it onto K-space. So now we get to this point. Now, I told you that there's this analogy, or like how do you call this, like reciprocity, that the RF basically deposits energy in K-space, and when you read out that energy from K-space. So your image is reading out the energy K-space, and then the RF actually deposits energy in K-space. If we deposit a sink, effectively we are exciting a rect. And the signal that comes from a rect, if you remember, in K-space is a sink, right? So we're depositing a sink, and then afterwards we're reading the sink, effectively. So at the end of the RF, it's also what we'll get is the signal that we just encoded. And if you notice, at this time point, we actually encoded an RF that is pretty much 0, right? So when we are in excitation K-space and also in readout K-space, our signal is effectively 0. And so this is also why we don't get any signal whatsoever immediately after the RF. And we need to have some gradient afterwards such that the signal then would increase to a certain level. And usually here we stop and we perform imaging in the other 2 dimensions, right? At this point, we usually stop when our signal is maximized. At this point, the signal is maximized. That's the maximum signal that would come out. And as it turns out, this is exactly when this is half the area of this, right? And from a K-space point of view, yes, this is the part where we move to the center of excitation K-space, but it's also the center of readout K-space. So that's where my signal is going to be the highest. And so if you think about it, you know, we excited this, but then we didn't get any signal whatsoever. Then we apply some gradient, then our signal will increase, then it would decrease, again goes to zero, and then increase to the maximum exactly when we have this area correspond to this area. And of course, you can go and do this analysis from a K-space point of view, because if we have the slope over here, that means that we are going to center our RF around the center of K-space. Then I had this exercise, and I did this before, so let me just do a different exercise now. Yeah, I had this exercise, and I asked, what does this pulse does? Okay, or what does this do? So we have a sync RF pulse in the presence of this gradient. What is the difference between the previous gradient that we use? Here it was positive, and then there's a refocusing, but I added an extra gradient before. And the question is, what does this do? And so we can go, the way that it works is what we need to do is we need to map the RF onto K-space. We know what RF is a function of time. We know what is K-space as a function of time. So now we need to find, we know what the gradient is a function of time. So now we need to find what K-space is a function of time, map the RF onto K-space, and then take a Fourier transform of the results that we get. Okay, so what is K-space? Well, it's always the area of the remaining gradient. And so what we do is we just integrate it backward. We first have negative, like start at always at zero. We end always at zero at kz equals zero. And then this is the area of the remaining gradient up to this point. And now this is the area of the remaining gradient up to this point. And then this is the area of the remaining gradient up to this point. And so if you think about it, the RF is just being deposited from positive kz to negative kz. Okay? Where kz is positive all the way to kz negative in a constant velocity. Okay, so what I do is you can actually go and figure this out. So we start at the center of K-space. We don't deposit any RF. We go to the positive, and now we start depositing RF. And then at the end, we move back and say, okay, this is kz equals zero. Okay, because of this extra lobe. And now we're going to take the Fourier transform of this. And what's the Fourier transform of this? I can't hear anybody.
Correct.
Yeah, it's erect. So the Fourier transform of erect, it's erect even without any phase because it's exactly centered around kz equals zero. Now, what did this do? I mean, it took me in the beginning from the center of K-space all the way to the edge. But that would have been true even if this didn't exist, then this would go away. Remember, it's always the area of the remaining gradient. So if we have RF, if we have a gradient before the RF, it doesn't do anything. Any gradient before the RF does nothing. Okay? Let me just say something that you would very often see an excitation pulse look like that, with a lobe over here and a lobe afterwards. And the question to you is like, why would you still have that added? That's a big mystery, huh? Okay, well, it depends how you program things, to be honest. If you remember, I mean, when we do imaging, we actually break into repetitions, right? Like we do with excitation, slice excitation, and then we do a readout, and we wait till the end of the TR, the repetition, and then we repeat again. We do another excitation, and so on and so forth. So effectively, don't forget that there is another gradient that is going to then be played, afterwards with an RF and then another readout, right? In the second one. So what you can think of actually the slope over here, the slope over here is actually the end of the previous TR. Okay, so you can actually think of a repetition that starts from here all the way to here. And sometimes we would like to add this at the end. I know I'm not going to tell you right now why we would like to do it at the end, but effectively, if now I integrate the area of the gradient, like I integrate this and I integrate that, that cancels half of that area. Well, sometimes before the next TR, sometimes it's useful to make sure that the area under the gradients is 0. So that's why we add this, because then if you integrate the entire thing with this thing, it will be 0 before the RF starts. Okay, the area underneath the gradient is going to be 0 before the next RF starts. Does that make sense? There is a reason to do.
Sorry,
I'm
are
not
you
going to tell you
saying?
right now why.
Okay.
But go ahead and ask.
So you're adding like that circled portion at the end, like after your readout, right?
Well, okay, you can call it. So this, so this will be after the readout, but because it's really close to the next RF, then often people just program it such that you have a low before this, and then the TR ends here and starts here. But you can also think of the repetition that that starts from here to here. It doesn't really matter,
Mm-hmm.
So from a programming point of view, people sometimes add this to the RF. But really what it is it's for the previous repetition.
Okay.
Okay. Let's do this. What does this do? Let's draw a K-space. First thing is we know what B1 is a function of time. We know the gradient is a function of time. Now we need to compute KZ is a function of time. So let's do that. Yeah? Okay. So that's KZ as a function of time. So we start at positive KZ. We cross all the way to the left, and then come back while depositing this. Okay, so let's do that. Okay, I'm gonna first do this part. Okay, up to here. So I'm starting from the right hand side. I'm going to deposit half a sink. Right? Half a sink of RF. And then nothing. So I keep on going, nothing, 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 right? And then I go back and deposit a sink, half a sink, right? When I go back. Okay. And this is KZ equals 0, right? That's where I finish. I finish at KZ equals 0. So the Fourier transform of that is rect. Yeah, that's another way. That's another way of doing a rect excitation. Huh? Pretty cool, huh? I know. There is an interesting advantage to this. First of all, when we finish here, we end up at the center of excitation K-space. So after this part, there's no delay. We immediately can image, right? We don't need to, like before when we had like, this part, then we had the dead time. Right now, there's no dead time. I can immediately do the imaging because I'm at the center of KZ. So from a T2 point of view, like if T2 is short, this is maybe a possibility to leverage this. Okay. So yeah, this should work. Now, if there is some decay that's happening while, and all sorts of other things, then, some of our assumptions are going to be violated. But to be honest, yeah, this actually gives us a slice selective excitation the same way that, doing a sync over here with the refocusing would do. Pretty cool, huh? All right, that's a good one. What about this one? Let's see. We know B1 is a function of time. We know gradient is a function of time. Now we need KZ as a function of time. Let's do KZ as a function of time. Area of the remaining gradient takes me from here to here, and then takes me from here to here, and then takes me from here to here. Okay? So period 1 goes from K-space being 0 to K-space being positive. And while doing that, I'm depositive and negative half sync. Okay? From the center all the way to the positive edge, depositing a negative half sync. Now I'm starting to go from the positive all the way to the negative, right? Positive all the way to negative. While doing that, I'm depositing a positive sync. Okay? I'm going to use a different color. Okay? And continue on with the other side of the sink. And then in period 3, I'm going to go from negative K all the way to KZ equals 0 while depositing a negative half sync. Okay, I sum these up. What do I get? 0. So what is the slice profile? Not excited. This is a waste of energy. We moved spin up, we moved them down, and put them back in the right place. Basically, that's kind of what we've done here. You flip the spins and then you put them back in the right place, and you pretty much did nothing. This is a pulse that does nothing. Does nothing for static spins. However, if you have a moving spin, then maybe things will not cancel between the two halves, right? If your spin is moving a little bit, then things may not cancel perfectly. And that could be a velocity selective RF pulse. It will select only spins that are moving as opposed to spins that are not moving. Pretty cool. I know. RF is pretty amazing that you could do it. Okay, any questions?
Can I clarify one thing, Mickey? So I understood that we are getting the signal at KZ equal to 0, and that's the only value of KZ we want to scan the slice for. Is that what we are doing here? And then we are going to vary KX and KY. And
yeah, when you get to KZ equals 0, you get the maximum signal from the slice.
I see.
because that means that there's no phase across the slice. And so the signal that you get is a sum of the entire slice.
I see.
And so you get the maximum signal.
So we
So
don't
gonna
get
be
any signal from any other value of kz, just kz equals to 0 is enough.
Yes.
Okay.
Now we're gonna give you a question, one of the homework, with an excitation that is actually a minimum phase pulse that looks like this. It's not a sync, it's kind of like a one-sided. And you have the RF, and then you have the gradient, right? The gradient will be on. And then the question is, how big should be the refocusing? Like where you should refocus to. What you really want to refocus is you want to refocus such that the peak of the RF ends up at kz equals 0, because that is going to be the maximum signal when you average across the Z.
I see. Yeah.
Okay, I gave you a solution. Now for some homework problem I will give you in the future.
Thank you.
Okay, so it's worth coming to class. Okay, so that's great. Oh, let's do this. This is exciting. This is exciting. Exciting, double exciting. Why? Because first of all, we have excitations. The result is exciting, and we're gonna excite something, right? So it's like doubly exciting. So here's a situation where I'm going to do two things. I'm going to excite an RF pulse like this, do some imaging, get the data. And then I'm going to excite with an RF pulse like this, do some imaging, get the data. Okay? And then I'm going to take those two images and I'm going to add together. Now, because this is all small flip angles, this is all linear. It's linear. It's linear even if we separate these into two images. And the question is, what is the effective slice select of these two excitations together? Ooh, crazy, huh? Check this out. Okay, so let's see. What is KZ? KZ starts at 0 and then it's positive. So basically at t equals 0, it's positive and then it goes all the way to 0 while depositing half a sync. Yeah? What about for this pulse? For this pulse, it starts here and then it goes negative, right? So it starts at negative kz and then we go to 0 while depositing half a sync. Okay. Okay. So let's do that. We start at some positive and then we're going to deposit a sync, right? Yeah. And that's it. We end it here, right? And this is kz equals 0. What is the Fourier transform of this? Remember when we did the imaging and we only imaged from the center out? And I told you that the real part is going to be like a rect, but then it has like an imaginary part that's big. You know, it's the same thing, but now in excitation. So effectively, Z will have a real part of spins that would look like a slice select. But it will also have an imaginary component that looks like that, I think. Something looks like this. Something like that blurs it. So it has an imaginary component because this is supposed to be, I mean, it's not symmetric around 0, so it has to have an imaginary component. Okay, so what is the situation though here? For this case, we start at negative and then start depositing RF. So we actually start to here. We start here, and then we end up here at kz equals 0. Now, tell me, what is the Fourier transform of that? The Fourier transform of this, the real part will be exactly the same. But the imaginary part will be exactly flipped. So what happens when you add these together?
Imaginary part cancels.
Yeah. So the signal that comes outside of the slice, I mean, this is the excited signal that's outside of the slice. But this is also excited signal outside of the slice, and their contribution will cancel. So effectively, anything that was excited outside of the slice will have its signal canceled, and will effectively excite a rect. So it would do exactly what we want. And we're doing that with 2 excitations. Now, why would we ever want to do that? Obviously, there could be a problem, right? Let's say we do this, it excites some stuff outside of the slice. We do this, but let's say there was motion between the two. Now it's inconsistent. So now when you add 2 things together, they don't exactly cancel. So you could see a problem with that, right? But why would you want to do that? What if you want to image something that has a T2 of 1 millisecond? How long is the refocusing? Compared to 1 millisecond, it actually could be long. And during that 1 millisecond, our signal can actually decay quite significantly. And so this, by doing this, is effectively, we can immediately image, let's say a radial trajectory, immediately as the RF finishes. Like switch immediately, and this is called half pulses. That's to image very short echo times in slice select acquisitions. Okay, this is to image a species that decay very rapidly, like tendons, for example. It's a typical thing that you'd like to use. Does that make sense? Because immediately after we're done with the RF, we can, do a radial trajectory, and then, and then repeat, a second one, and then repeat this. It costs us twice the scan time when we do that, because we have to collect 2 images. But then it allows us to do very, very short, what's called echo time. So image with very little delay between the RF and the readout. This is also John Pauly. Had a pretty successful PhD thesis. Not bad, huh? Developing excitation K-space, half pulses, and also the Shinnar-LaRue algorithm, which we are not going to talk about. Okay, so this is analysis. You have now the idea how to do an analysis. I can give you an RF pulse, I can give you a gradient, and you can then go and do an analysis. What is the slice profile? Are you confident you can do it? Well, if you're not, Ekin, why don't we just give them some homework to solve some, similar problems so they can do this analysis? What do you think?
Sure, yeah, there is already
Oh,
assigned problem.
Okay. Well,
How convenient.
you get an exercise on this. How convenient. Which was also given in one of the midterms. By the way, we decided we're not going to do a final or a midterm. Is that okay? Are you okay with that? Any objections? I might change my mind though. But as of today, it looks like chances are going to be the grading is going to be based on the final project, is going to be based on the labs and based on the homework. And we're going to do an fMRI scan of every single one of you, and we'll test how excited you are about MR, and that will be also part of your grade. So you should start practicing.
When will we get to the project part? Like get the prompt or?
Yeah, before we're gonna release some information before spring break, I think, right? We have to, right, Ekin? Otherwise,
Yeah.
we're not in a good shape.
Yeah.
Yeah. Okay, so analysis, now let's talk about design. Here's the thing, once we understand that we can map B1 to K-space and then compute Fourier transform in order to see what the slice profile is, that is also a recipe for design, because now I can go backwards and say, oh, here's the slice profile I want. Okay. Let's go and design a gradient that traverses K-space appropriately. And now all I need to do is design the RF that's this case, and I can make an RF pulse that meets my specs. It comes down effectively to a filter design problem. If you just want to do slice select, right? Because it's it's some singles, and it's going to have some ripple. It's going to have some rip in the pass band and ripple in the stop band. It's pretty much a filter design problem, a digital filter design problem. Isn't that amazing? Who's studying EE123 or studied in the past? Yeah. So now you can kind of like, oh, that's kind of useful, right? Because effectively, this is what it is. So effectively, what we want to do is we want to choose a B1 of time, B1 of t, which has a nice transform. Okay, for example, it should be a sync. A sync will give me a perfect slice selection. But unfortunately, sync, of course, is not practical because sync is, continuous and infinite. So that's a problem. Okay, it's continuous and infinite. And what I want really is I want a finite pulse. So, and of course, I'm going to digitize it because I'm giving those numbers to the hardware in order to generate the pulse. So what we could do then is we can say, you know what? I can take a sync, but then I can also truncate that sync, let's say with the rect. So sync of t times rect of t over 2n will then be a cropped sync. Here, 2n means that I cropped it at the I guess this zero crossing or something like that. And then the Fourier transform of this would be then a rect, but that rect is going to have ripple both in the stop band and also in the pass band. Now, what's the consequences of having ripple for our case for slice selection? Well, in the pass band, that means that our slice is not uniform. Is that a big deal? Well, the slice is thin, then this doesn't have a huge effect, because if you think about it, we average across this anyway. So if it has a little bit of a ripple, it doesn't make a huge difference in terms of image contrast, at least if the slice is pretty uniform across. Then it definitely doesn't make a huge effect, but it does a little bit. What about the stop end? That means that I'm going to excite stuff outside of my slice. And that could be a problem. Definitely, definitely if these are strong signals, that means that I'm going to lose my resolution because, my signal is going to be localized. It's going to have information, far away from the slice. But also, if I excite stuff outside of the slice, when I excite the next slice, this has already been excited. So I'm going to have some steady state issues. Your recovery time is not going to be perfect. So it's gonna be inter-slice problems. Okay, so it's too much ripple. So what's the usually solution to mitigate with ripple?
Different window.
Yeah, different way. So for example, we can pick like a handing window, a hand window, or pick your favorite window. Now it's some window, and now my slice profile is much nicer, both in the stop band and also in the pass band. Except that my transition now is a little bit. The transition width, of course, is now more broad. So my slice is not really that active. It's a little bit broad, and so it's going to have some transition width that we need to understand that exists. And normally we'd consider this to be the slice thickness, but we have to understand that this part is going to be partially excited, and this part is also going to be partially excited. Okay, and going to contribute. And this part over here is also going to be partially excited. It's not going to be fully excited. So we have to understand that. Okay. All right. So now the question then is how much of that sink we're going to be using. And there is a really nice way to characterize those pulses by a notion which is called the time bandwidth product. And time bandwidth product is pretty much what it is you take the time, like if you want to characterize a sink pulse or a windowed sink pulse, what you do is you look at how long that pulse is, and then look at the bandwidth of that pulse and multiply time by the bandwidth. And that would give you pretty much this product. Now, as it turns out, the time bandwidth product also corresponds to the number of zero crossings of a sink. So for example, a time bandwidth 2 pulse will pretty much have 2 zero crossings. So it's just the main lobe of the Windows sink. So it has 1, 2. Okay, 0 crossings. Time bandwidth 4 will have 1, 2, 3, 4. So it's just another cycle of that sink. Effect. This time bandwidth 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and time bandwidth 12. Basically, we get more and more of our sink. Okay, as you increase the time bandwidth. Now, of course, if we window a lot, with time bandwidth 2, the slice is not going to be very rect-like. It will be more, has more of that kind of a shape. The higher the time bandwidth is, the more it's going to look like a rect, because the more this post looks like a sink, then its Fourier transform, the slice profile, is going to look like a rect. Okay. Now, time bandwidth 2 is often used for rapid imaging, because you can achieve a very broad bandwidth for a very short time. Okay. Time bandwidth 4 is usually done in order to do like 180 inversions or 180 spin echoes that we talk about later. If you're going to do a 90, then maybe time bandwidth 8. And if you do slab select, if you select a volume, or actually if you're just interested to excite and saturate a particular part of the volume, not for imaging, but just to kill the magnetization there, then you would use a very high time bandwidth, like time bandwidth 12, for example, or even more. Okay. Now, the nice thing about this, if we know what the time bandwidth of the pulse is, let's say time bandwidth 2, if I knew what the time is, I can then calculate the bandwidth very easily. Let's say a 1 millisecond pulse, that's time bandwidth 2. What's its bandwidth? Time times bandwidth equals 2. Time is 1 times e to the 10 to the minus 3. times bandwidth equals 2. So bandwidth equals 2 divided by 10 to the minus 3, which is 2000 hertz. Okay, so it's very easy. So the slice profile is going to look, not very selective. And from here to here is going to be 2000 hertz. If this was 1 millisecond. Does that make sense? So it's really, really nice way of thinking. Now you can just eyeball a pulse and, oh, it's 1 millisecond, it's time bandwidth 2, because you can eyeball it, you can count the zeros. You know exactly what's the bandwidth of it. And now you know how many hertz, what's the bandwidth it supports. And of course, if you want to map that into a slice thickness, then calculate what is the gradient amplitude that maps 2000 hertz into, let's say, 1 millimeter or 2 millimeters or so on, whatever slice thickness you are. And that allows you to do a design. Huh? Really nice. So that's the difference between the slice profile of time bandwidth 2, and this is the slice profile for time bandwidth 12. Okay, so obviously this is not like a rect, and this is more like a rect. Okay. All right. So now the question: if we fix the bandwidth and make t longer, what would happen to the pulse, to our slice selection? Okay, what would happen? So this is time bandwidth 4. That is half the length as time bandwidth 8. Okay. So I don't know. Let's say that this is 1 millisecond. Just for the sake of it. And let's say this is 2 milliseconds. Okay. So 1 millisecond times bandwidth equals 4. And here 2 times bandwidth equals 8. What's the bandwidth for these two cases? The bandwidth is the same, right? So for the same gradient amplitude, it will excite the same slice thickness. And if you can actually see, the slice thickness is similar. It's the same between the two. Okay, the slice thickness is the same between the two. The difference is that this one is just more selective. This one is more smooth, it spreads out. But because we use the time bandwidth 8, now our slice is more selective, but it's the same width. What was the cost to get more selective? Time. My pulse is longer by a factor of 2. That could be a problem, right? That could be a problem because it costs me time. During that time, a lot of things can happen. Signal can decay, all that kind of stuff. Okay. All right. Okay. So if we fit bandwidth 80 longer, then we get the same thickness but sharper transitions. Now the question is, if we fix the duration now is the same. It's 1 millisecond. And then it's 1 millisecond. Okay. The duration the same, but we doubled the time bandwidth. What would happen? Well, 1 millisecond times bandwidth equals 4. And then 1 millisecond times bandwidth equals 8. What's the bandwidth in this case? It's 4 kilohertz, right? And here it's 2 kilohertz. or no, sorry, here it's 4 kilohertz, here it's 8 kilohertz. That means that for the same gradient amplitude, this will be half the thickness as this one. Okay, same time, double the bandwidth, I get double the slice thickness. Okay, and you have to actually, what's also interesting is that this shape here is exactly the same transition as this. Kind of makes sense too. Okay. All right. Any question? Now, typically in MRI, we usually fix the duration of the pulse. We say, you know what, the pulse should be, 2 milliseconds. That's it. We're not gonna make it bigger. And what we do is we adjust the graded amplitude if there is any increase in bandwidth. For example, if you have a time bandwidth 4 pulse, let's say for 1 millisecond, and this is 1 millisecond. This is time bandwidth 4 pulse, okay, for 1 millisecond, and with a certain gradient, right? That would then excite a slice that looks like time bandwidth 4. It has a shape of time bandwidth 4. Now, if I apply a time bandwidth 8, same time, now I have double the bandwidth. I have double the bandwidth, but then I also double my gradient. That means that now my slope in the same if I double the gradient, then the same width would correspond to double the bandwidth, right? Doubling the gradient will double the bandwidth of the same width. Hence, if I double the bandwidth and I double the gradient, I keep the slice at the same width. Does that make sense? Or my logic was convoluted?
I'm a little confused. Do we want a thicker slice? Is that, I would think that we want a finer slice.
I don't know. It depends.
Okay, so it depends. All right.
Katie, let's say you want to go scan, right? Like you want to
Mhm.
scan a heart.
Yes.
Okay. You want the thinner slice possible, so you prescribe a 0.0001 millimeter slice.
Mhm.
Okay, that's very small. First of all, the scanner probably will go and complain about it. But let's say it doesn't complain, that means that your RF pulse is going to be very long in order to be so selective, because your time, is going to be like you're going to have a hard time to do that, right? So you're going to have a very long pulse. So that's a problem. Okay, but let's say the scanner scans it, and you scanned with your 0.00001 millimeter slice, right? And you get some signal, and you get an image, and you look at this image, and then you call me, or you come to my office hours, because you're going to have a problem. And the problem is you're going to go like, hey, Mickey, look, I scanned with a 0.00001 millimeter slice, and I thought the resolution is phenomenal. But I look at this image, and all I see is.
Would you see a lot of ringing or like blurring or no?
You know what you'd see?
What? Nothing?
You'd see noise. You'd see noise because in a 0.00001 millimeter, there's very few spins. It's not even useful enough to overcome noise. So that's another consideration. The slice thickness also is one way to boost up SNR. You lose resolution in the slice direction, but you boost SNR because now you get signal from like a larger volume. So for example, for cardiac imaging, sometimes it'll be 5, 6, 7, 8 millimeter slices thickness in cardiac imaging. Brain imaging, it's usually 2 millimeters, something like that. The slices would be, something like that. So the question also is like how selective the slices. I mean, obviously we would like the slices to be very selective, but sometimes, besides, we also want to keep the RF short, and so it's competing. Okay, but typically we want to fix the RF, like the RF. If the RF is fixed, sorry, if the length is fixed, and let's say you want to go from like a more selective slice, let's say from time bandwidth 4 to time bandwidth 8. If I do the gradient and I change the RF, then I keep the slice thickness to be the same. And I can have lots of questions like this, we make the RF twice as long and increase the height by factor. Also, by the way, the height here has to be double, because otherwise there's not enough energy to do a 90-degree. Right, like you need to integrate this and see, if it's too squeezed, there's not enough energy. So you also have to double its height, and eventually you're going to hit also RF amplitude limitations as well. So there's all sorts of considerations here. I mean, as long as you can, you're going to increase the gradient and then increase the RF amplitude. But let's say I now want to go to time bandwidth 16. Time bandwidth 16, I need a gradient that's 4 times as big as this one, right? Maybe that's going to violate my gradient amplitude. And then I will need also a peak RF that's also 4 times as this one. I might also hit the RF amplitude limits. So there's all these considerations. And this is why pulse sequences are, like they shouldn't be so complicated. I mean, like you just put RF here, gradient, but then you have to take into account all those options. You want that kind of slice thickness with that shape and all of that, and that hit the gradient amplitude. And so then you have to calculate all sorts of things to make sure that it works, and the timing, and it gets longer and less. So that's where pulse sequences can become complicated because of all these ifs and cases. Let's do this one. This is a real problem. Consider a time bandwidth pulse with 2 millisecond duration. Okay, time bandwidth 8. How many zero crossings?
8.
8. Beautiful. Paying attention. That's nice. Thank you. What is the gradient amplitude that results in a slice thickness of 1 centimeter? Okay, so effectively, what we have is we're going to apply this gradient. Okay, and we're going to apply an RF that's time bandwidth 8 during the flat part of this gradient. Okay, and the question is, what is this gradient amplitude? Okay, for 1 centimeter slice. How do you even know about it? Well, you know the time bandwidth. Hello? 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 It says my internet is unstable.
We can hear you fine. Or at least I can.
Yeah, no, I agree. I mean, I'm connected with a gigabit. With a wire. I mean, like, how can... this company at? You know that company at? Sometimes very disappointing at company. Okay. Yeah. You should complain to At. Anybody here has the internet from At? My wife is shouting, Mickey, it's not funny.
I think it's funny.
Nate, they think it's funny. Or at least one person. One person thinks it's funny. MRI scientists, they might have a similar sense of humor as I do. She doesn't find it funny. Okay. Yeah, how do we go about it? Well, okay, we know the time, we know the time bandwidth. So then from there, we can figure out what the bandwidth is, right? If we know what the bandwidth and we know how thick is the slice, then that would let us figure out what is the gradient that would match this bandwidth for that particular slice thickness. Okay, this is how we're going to do it. So time times bandwidth equals 8. Okay, 2 milliseconds times bandwidth equals 8. That means the bandwidth is
4.
for what?
Hertz or kilohertz or something.
Kilohertz.
Kilohertz.
Yeah, because that was milliseconds.
Yeah.
Okay, what is delta Z? The slice thickness?
One second.
1 centimeter. Okay, so what is the bandwidth? The bandwidth. Fine. I'm not going to write it again. I've already prepared. The bandwidth is equal to 4 kilohertz, but it's also gamma over 2 pi g times delta z. Okay? The bandwidth is 4 kilohertz, but it's also gamma over 2 pi g times delta z. Delta z we know, 4 kilohertz we know, gamma we know, 2 we know, pi we look it up. Actually, we don't, because we know what is gamma over 2 pi. Gamma over 2 pi is 4.257 kilohertz per Gauss. Okay, so 4.257 kilohertz per Gauss multiplied by Gauss times 1 centimeter is going to give us a gradient field, which is 0.94 Gauss per centimeter. Woohoo! Now I can design an RF pulse. That's easy. That's easy. Okay. How do I make sure that the RF pulse will produce a 90-degree flip angle? What happens in the center of the magnet? Do the gradients do anything? No, right? So there, the flip angle is just the integral over this, right? So the integral over that should give me theta, 90 degrees. So gamma times B1 times 2 milliseconds should give me pi over 4. Does that make sense? Integral of that. I mean, remember the spins precess about B1. At the center of the magnet, they just precess about B1. So, and because there at the center of the magnet, angles add because we're only applying B1x. And so if I just integrate that, I want the integral of this, gamma times B1 times tau, 2 milliseconds, to be equal to pi over 4. Does that make sense? So then I know now, what's the shape of that should be. You know, I can design, you know, a windowed sink of, you know, I'm going to design a sink. I'm going to window it. Then I'm going to integrate it, and I'm going to normalize it such that it's going to be 90 degree. Then I'm going to apply a gradient, which has an amplitude of 0.94 here. Then I'm going to design the ramps that reach this 0.4, right? That obey the slew rate. And then all I need to do here is to come up with an area gradient that has half the area of this. There you go, voila. I've now designed an RF pulse. That gives me what I want. Okay, so now the question is, what delta Z, the desired delta Z, is 0.5 centimeter. What would happen then? What's my gradient that needs to be for this to happen? I need half the thickness. What do I need to do to the gradient?
You need to
Double it, right? If I double the gradient amplitude, the same bandwidth is going to map into half the slice. Okay? All right, that's great. But, so yeah, so the gradient is going to be 1.88 Gauss per centimeter. But what if G max, the maximum gradient, is 0.94? Like I cannot increase it, but I still want to make a slice that it's half. So what do I do? In case I need to reduce the bandwidth, right? I need to adjust the bandwidth. That's the only way. I need to adjust the bandwidth.
Would you increase the time?
That's one way. I can increase the time. If I double the time, that would work. Or keep the time, but how do I reduce the bandwidth by a factor of 2, keeping the time?
Remove a
Time
zero
times
crossing.
bandwidth. Time times bandwidth. I need to reduce my. Somebody says zero crossing, but yeah, but that's a the zero crossing is there's an indication for something, for some measure. What is it? Folks, speak up.
Is it the width of the like the main lobe, or I don't know. Because wouldn't that affect the zero crossing?
Look, we have a pulse, right? That we know that for 2 milliseconds, it produces 4 kilohertz, right? 2 milliseconds produces 4 kilohertz bandwidth. Then we set up the gradient to be 0.94. That results in 1 centimeter thickness. Okay. Now, if I increase the time, and I keep the time bandwidth, then my bandwidth would decrease by a factor of 2. Right? If I double the time and I keep the time bandwidth the same, then my bandwidth is going to reduce by a factor of 2 and my slice is going to be half as thick. Alternatively, I can keep the time and reduce the
Thickness of the
bandwidth. I can reduce the time bandwidth. And now my slice is not going to be selective, so selective, but it's still going to be thinner. But select. Do you see the trade-off? So I can play with the time bandwidth of my pulse. I can play with its time, right? And I can play with the gradient in order to control. All these three control my slice thickness. And the trade-offs, of course, you know, the higher the time bandwidth, the more selective it is. You know? That's it.
When you say to
Okay.
reduce the TBW, what would that look like physically?
This is time bandwidth 2, this is time bandwidth 4, this is time bandwidth 8, this is time bandwidth 12. And the effect on the slice thickness, on the slice is that, you know, like time bandwidth 2 is not very selective, but time bandwidth 4 is very selective. At 12, you know, is very selective. They look more like a rect. Okay,
I have a
so
question.
I can make, yeah.
What about changing the amplitude of the peak of the RF pulse? Where does that come in?
That changes only the flip angle.
For the same
Like the
time?
amount of RF, right? The amount of RF for the same amount of time would only change the flip angle.
Okay.
Right, because just think about it. Again, think what happens on isocenter where there's no gradients.
Oh yeah.
You know what does the amplitude does? It's really useful to think about that.
Yeah.
That way. What happens to the center of the magnet? You know, that's, you know, then you remove all the gradient stuff and then, oh yeah, it's simple.
So when we talk about a flip angle, does it, is the flip angle, do we really just talk about it at isocenter?
Not necessarily, because it's a sync, you know, because it's a sync pulse, it's a rect in the other domain. So if you know what the flip angle here, you know what the flip angle here, you know what the flip angle here, you know. But you know, you can calculate very easily what's in the middle. You know. Also, you can compute the Fourier transform. Yeah.
So is the flip angle the same across the field of view?
No, I mean it has ripple, right? Because it has, depending on what is your slice ripple.
Oh, okay.
Right. That's you can control it by controlling the time bandwidth and the type of window that you use. It's basically it's a filter design problem. That's what it is. Okay, so what does this pulse do? Well, we can do it, right? Like this goes like this, right? You map K-space. Okay. So effectively, we go from the center of K-space, move to the positive side, then the positive is sync all the way to the negative side, and then back to the center. And then we go from the center, go to the right side again, deposit another sync, and then back to the center. Move right, deposit another sync, move to the left, and then back to the center. And then move right, deposit another sync, all the way to the left, and then deposit. So effectively, you go like this, you move to the right, then you deposit a sync, then you go back to the center. And then you go right, and you deposit another sync. That adds to it, right? That adds to it. And then you go back to the center, and then you do it again. And then you do it again. So what does this do? And now this point over here is kz equals 0. So if each one of these produce a theta flip angle, what does the entire pulse does?
For theta.
For theta. That's right. It does 4 theta. Pretty interesting, huh? But why would anybody want to do this? Let me just tell you something. And we're going to finish today. And I'm going to leave you with a little bit of a, you know, some wondering to think of. Okay. Here's a situation. Okay. This is an R pulse as a function of time. Our gradient is 0. Kz, what is Kz then? Is 0 for the entire thing, right? So what is our excitation K space?
Is it just all at
What's our
0?
excitation? Well, you always stay at K0, right? So we're staying at K equals 0. Let's say this point is Kz equals 0. And we're just depositing energy at Kz equals 0. In the beginning, we deposit negative sand, negative RF sand. And then we start depositing positive RF sand that overwhelms this negative RF sand. And then there's a little bit more negative RF sand, but you know, the positive is way more positive than the negatives. So ultimately, there is some value. Where is it located? At Kz equals 0. How can you write that thing? What is this function?
Delta?
Yeah, it's an impulse function. And what's the height of the impulse function?
Be the integral?
It's the integral of this B1. Yeah, that's right. It's the integral of this B1. And what's the slice profile?
The whole space.
Yeah, so it's non-selective. So even though I played the sync pulse, you know, it acted on everything the same way. And so it just produced a constant flip angle. Interesting, huh?
I have a question.
So weird. Yeah.
What does it mean to deposit positive and negative RF energy, like physically?
Well, it's you know, it's a direction, right? It could be in direction B1x or negative B1x.
Okay.
Right? So, you know, they can cancel, right? Like there is a negative RF energy, right? Like electromagnetic waves, you know, like you can have a magnetic field that's positive and negative, right?
Yeah, okay, that makes sense.
Value. So this is not selective, right? This is not a selective pulse. Let me just do though a thought. But this pulse is not finite in time. It's like it has a it's not infinitesimally, you know, small in time. Like it actually has a length. Do you see that it has a length? Okay. So the real question is, what happens normally when I have a spin at some z position, if I have a gradient, that spin will precess at the frequency gamma over 2 pi gz times z. Do you agree? If I have a spin and I have a gradient, then that spin at position z will precess at gamma over 2 pi gz dot z. And so my k space, kz dot times z would be the integral from t to t, gamma over 2 pi gz dt times z. Okay? Do you agree? And this is how we got to k-space before. Okay, now my question is, what about chemical shift? What if I have protons that resonate at different frequencies? because of chemical shift, not because of a gradient, because of chemical shift. Let's say a spin, because of chemical shift, precesses delta F frequency offset with respect to the Lamor frequency of water. Okay? Now, if it precesses at delta F, well, what I can do is I can write the same expression. Like before I wrote kz times z, now I can write k delta F times delta F, because a spin, look, a spin that precesses at delta F because of chemical shift cannot be distinguished from a spin that is at some position z with some gradient. Like there's no way to distinguish between them. I mean, there is one position where they're exactly the same frequency, right? So I can also then think about, if this is kz times z, I can also think of k delta f times delta f, which is really the integral from t to t of 1 times dt times delta f. So I effectively, I can think of time as the k space of chemical shift.
Oh, that's weird.
Time is the k space of chemical shift of off resonance frequencies. And so in that case, you know, time always passes, right? So I know that I end at k is equals 0 at the end, then my k delta f is going to look like this. And then effectively, what I am depositing a sink in kf. And that means that now, and this is now kf equals 0 is over here. So after the pulse is done, I can compute the Fourier transform of this and see which chemical shifts are going to be excited and which are not. And what's going to happen is that if I compute the Fourier transform, I will have some rect. And so there are, let's say, that rect is going to select or excite spins around some bandwidth. But let's say lipids are far away from this, they might not be excited. Lipids are 460 hertz or something away from water at 3T. So that may not be excited if I play the sync pulse such that the bandwidth only covers the water and maybe a little bit around it, but doesn't cover the lipid signal. So this is effectively a spectral pulse. The fact that, so it's not slice selective, but it's still frequency selective. It's frequency selective. Does that make sense? We'll go over this again next time. But now, let me just say something very quickly. What if instead of a continuous pulse, I'm going to do a discrete pulse made out of delta functions? How's that going to affect my spectrum? Well, multiplication by a delta train is a convolution with a
Comb.
with another comb in the frequency domain.
Yes,
So
it
if
repeats.
here was a rect, then I would have here and another rect and another rect, right? And another rect is being excited. Yeah? Okay. Okay, so now I have these impulses over time will result in this type of excitation over frequency. Now I can replace each one of those impulses, I can replace them with small sinks
can replace them with sinks, and I can add a gradient. Slice selective gradient for each one of those. So here's what happens. This gradient will select a slice in the z direction. But because these are also excited over time, it will also be selective in frequency. And this is called a spectral spatial pulse. I can excite a slice that only excites water and doesn't excite fat. Isn't that amazing? Okay, this is a two-dimensional pulse, effectively. It selects both the spectrum of chemical shift as well as being slice selective. And we're going to talk about it more. I got to run to physical therapy right now. So long. And thanks for the fish.